Okay, welcome back. So today we'll continue our discussion on genome assembly algorithms, and in particular we'll look at one of the formulations known as shortest common superstring. So before that, let me do a quick recap from the last lecture. So in the last lecture I defined the genome assembly problem, that is, you are given a large number of fragments or reads from the genome, and the goal is to reconstruct the original sequence back from where these fragments are derived from. So the genome assembly problem is to reconstruct the original genome sequence back from these fragments. We saw various challenges associated with genome assembly. So for example, we saw that in practice the challenges faced are repeats in the genomes. There are too many reads to handle. So we are working typically with large amount of data. We can have missing pieces in the data. For example, there may be regions in the genome where there is insufficient coverage. There can be sequencing errors. So in fact, many pieces you can think of them as damaged because of significant sequencing errors. And we don't know the final solution. So like in a jigsaw puzzle, you know how the final solution looks like, but in the genome assembly problem we don't know how the final genome sequence looks like, and that's the goal actually. So we want to reconstruct that original genome sequence from this read sequencing data. So all these challenges make the genome assembly problem interesting. In particular, in the last lecture we also focused on one of these questions: how much sequencing data is enough for genome reconstruction? Because I mentioned that typically in an experiment we can control how much data we want to generate, that is, how many reads do I want to sequence from the genome, and ideally we want to cover the entire genome sequence with these reads, and for that we had derived an expression in the last lecture that gave us an understanding of what coverage do we want from the read dataset, so that we can ensure that the entire genome sequence is covered. So moving on, as you can imagine, in the genome assembly problem, one of the key principles that we are going to use is going to be the suffix prefix overlaps among the reads. So for example, if you have a read 1 which has a significant suffix prefix overlap, that is such that there is a long suffix of read 1 that matches a prefix of read 2, then maybe we can draw a hint that maybe read 1 and read 2 are consecutive in the genome sequence as well. So most of the formulations for genome assembly use this principle that the overlapping reads should be consecutive in the genome sequence. Now these overlaps can be exact. So if there are no sequencing errors, then we can assume that the true overlaps among the reads should correspond to exact suffix prefix matches between the reads. But when there are sequencing errors, we may need to consider approximate matches as well. For example, if there is a sequencing error here, then maybe we need to allow some edits during matching as well. But for this lecture we will assume that there are no sequencing errors. In practice, genome assemblers would typically try to correct these sequencing errors before moving to the genome assembly problem. So for the purpose of this lecture we will assume that the reads are error free, and we will look at some of the formulations that can be used for solving the genome assembly problem. So the outline of this lecture is going to be as following. First, we will look at the shortest common superstring problem, which is one of the first formulations developed for genome assembly. We will look at a greedy algorithm for this problem, and in the next lecture we will analyze that greedy algorithm in more details. Okay. So let us get started, and let us understand the definition of shortest common superstring problem. So, as input we are given a set of strings which is denoted as f, right. So, these can be for example reads from the genome sequence, and as output we are looking for the shortest possible string s such that for every string in the set f is a substring of s. So, in other words we are looking for a shortest string s such that every string f in my collection is a substring of s. So, an example is shown below. For example, let us say you are given a set of 5 strings as input, then as output I am looking for the shortest string s such that every one of my input strings is a substring of s. So, for example, in this particular case every particular string, so for example you can see that CATG is a substring of s, CTAAGT is also a substring of s. Similarly, other strings are also substring of s. So, clearly all of these substrings are a substring of s, and in this particular case it turns out that s is of shortest possible length. So, for this particular example we cannot find a shorter string which will satisfy this property that every string in f is a substring of s. We can think of another example, let us say s double prime string. So, let us look at another string s double prime. Observe that in this case s double prime is a superstring, meaning that every string in f is a substring of s double prime as well, but s double prime is not the shortest possible superstring. You can clearly see that s double prime, the length of s double prime is larger than length of s. So, again you can verify that s double prime is also a superstring. CATG, again all the strings are substrings of s double prime, but in this case s double prime is not a shortest superstring. It is a superstring, but it is not a shortest superstring, whereas s is the shortest superstring in this example. So, I hope the definition of shortest common superstring problem is clear now, and this was one of the first formulations that was thought for genome assembly problem, and you can approximately see that this is following the parsimony principle, that is, given the set of reads I have observed, the intuition here is that maybe my genome sequence is the shortest possible sequence from which all of these reads can be sampled from. So, this formulation was based on the parsimony principle. Now, let us look at maybe how we can solve this problem. So, solving the shortest common superstring problem. First of all, we will make an assumption that the collection of strings that I have been given, that is set f, is substring free. That is, no string in f is a substring of any other string in f. So, for example, that means that I do not have any. So, for example, if f has a t c g and a t c g a, then this situation is not allowed, because here a t c g is a substring of the second string. So, we are assuming that f is substring free, that is, we do not have a string in f that is a substring of any other string. Now, observe that if f is not substring free, then we can easily make it substring free by iteratively removing all those substrings. And it is also easy to observe that if you suppose construct a f prime set which is now substring free, then the shortest common superstring for f prime is also a shortest common superstring of f, right, because all we did was remove the substrings. So, if I am solving this shortest common superstring of f prime, then naturally that is also a shortest common superstring of strings in f, right, because we only remove the substrings of the strings. So, from now on we will assume that the set f given to us is substring free. Now, next we will define something known as overlap graphs. Given a collection of strings f, the overlap graph, which I am denoting as OG, the overlap graph OG of set f is denoted as VEW, where V is the set of vertices, E is the set of directed edges, and W are the weight assignments on those edges. So, this is a weighted directed graph such that the set of vertices corresponds to the set of strings, that is, each string in f is a vertex in the graph. This is a complete graph, that is, for every pair of vertices uv we have an edge from u to v, right, except that we do not have any self loops. So, we do not have any edge from u to u itself. So, there are no self loops and it is a complete graph. Between every pair of vertices you have a directed edge. Finally, the weights in these graphs correspond to the suffix prefix overlaps between the strings. So, if you have two strings f1, f2, then the weight of the edge from f1 to f2 will correspond to the length of the longest suffix prefix match between f1 and f2, that is, the length of the longest suffix in f1 that matches a prefix of f2, right. So, this is the maximum suffix prefix overlap length and that will be the weight of this edge. So, an example is shown on the top where you have 4 strings and you see a complete graph, right. So, between every pair of vertices you have edges going both ways and the weight of each edge corresponds to the suffix prefix match between those two strings. For example, if you look at vertices b and d, then the longest suffix of b is ac, that matches the prefix of d. So, accordingly you have a weight of 2 for the edge going from b to d, and vice versa. Similarly, the longest suffix of d is of length 1, that matches a prefix of string b. So, accordingly the reverse edge has weight 1, and you can verify all the other weights of the edges and see that all those weights correspond to the length of maximum suffix prefix match. Some of these weights are also 0, that is when there is no suffix of a string matching a prefix of another string. So, in that case you will have an edge with weight 0. Okay, so that completes the definition of overlap graphs. Now, let me also tell you why are we discussing this overlap graphs, right, and what is the connection of these overlap graphs with shortest common superstring problem. So, for that I need to define something called as Hamiltonian paths. Now, for students in computer science background, they may already know what Hamiltonian paths are, but for others let me define what this means. So, Hamiltonian paths are those paths in the graph that visit each vertex exactly once, right. So, for example, in the example shown here, the path starting from B going to D, then going to C and then going to A. This is a Hamiltonian path because it visits each vertex of the graph exactly once, right. So, similarly a path starting from D, C, B, A is also a Hamiltonian path because it visits each vertex exactly once, and you can easily see that there are exponentially many number of paths in this graph, right. So, we can have many Hamiltonian paths. So, these are the paths that visit each vertex exactly once. Now, let me define also the string spelled by a path. So, the string spelled by a path denoted as capital SP is the string spelled by that path where we use the overlaps only once. So, the suffix prefix overlaps between the consecutive strings will be used only once while I am spelling that path. So, for example, if I spell the path corresponding to path BDCA, then I would start by spelling ACTAC, but then I would not consider the first two characters of D because that correspond to the overlap which I have already considered here. So, then I would spell GGA, that is the remaining characters of string D. Then in my next string there is a overlap of 4. So, I would only spell CT. So, I will not spell the overlap again, and then finally moving to A, there is a overlap of length 1 and I would spell the remaining 3 characters. So, I hope this is clear, that is, this is the string spelled by the path, but we are not counting the overlaps twice, we are only counting the overlaps once. So, formally I can write SP as following. So, for a given path P F1 F2 let us say until Fk, the string spelled by this path will be F1 concatenated with the last few characters of F2, that is the last few characters, basically last characters subtracting the overlap length. Similarly, the last characters of F3 subtracting the overlap length and so on. So, here plus denotes the concatenation operator. So, this is just to what I just said, this is a formal definition of the same thing. Now, here comes the connection between Hamiltonian paths in the overlap graph and the superstrings of a string set. Here are the 3 questions that I want you to think about. Does every Hamiltonian path in the overlap graph spell a superstring of the set F? The second question is, does every superstring of F correspond to some Hamiltonian path in the graph? And the third question is, does a shortest superstring of F correspond to a Hamiltonian path in the graph? Maybe at this point you can pause this video and think about all these questions yourself first. So, let us start with the first question. Does every Hamiltonian path in the graph spell a superstring of F? Well, if you think intuitively, because Hamiltonian path visits every vertex, that is it considers every string in the set F. Therefore, because we are visiting every string, the string spelled by the Hamiltonian path will be a superstring of F. So, this is obvious, and you can simply prove, if you want to prove, you can easily prove by contradiction. Now does every superstring of F correspond to a Hamiltonian path? Well, not necessarily, because I have in a superstring I can always include a specific string twice, thrice, 4 times. There is no specific restriction on that. So I can always form a superstring. For example, if I have 3 strings F1, F2, F3, then I can simply concatenate F1, F2, F3, and then I can again concatenate F1, F2, F3, and I can form a long string which includes every string twice. In that case, this won't correspond to a Hamiltonian path. So the answer is no, because a superstring can include a string twice or thrice, as many times as we want. Does a shortest superstring of F correspond to a Hamiltonian path? Well, yes, but why? Here, if you think intuitively, you may see that it should be true, but for this question we have to provide a proper proof, because this is not an obvious property. So let us look at this particular question in more detail, and this question will help us establish a proper link between shortest common superstring problem and the Hamiltonian path problem. So the Hamiltonian path problem is a very standard problem in graph theory. So by building this connection, we have at least one way of solving the shortest common superstring problem. So let us try to prove this property 3 in the next slide. So the question is, does a shortest superstring of F correspond to a Hamiltonian path? The answer is yes, and here is the proof. Let us say that capital S is a shortest superstring of F. So I am considering a shortest superstring of set F. Next, let us consider any 2 strings Fi, Fj from F, and let us find their occurrences in S. Because S is a superstring, it must have Fi and Fj as substrings. So there will be intervals in S which correspond to Fi, and there will be some interval in S which corresponds to Fj. Let us consider those intervals. Suppose now, once we define those intervals Fi, for one for Fi and one for Fj, suppose let us say the ending character of Fj, so the ending character of Fj occurs after the ending character of Fi. Let us say that is true. Then the starting character of Fj must also occur after the starting character of Fi. So what I mean to say is that if the ending character of Fj is occurring after the ending character of Fi, then the starting character of Fj must be occurring after the starting character of Fi. That is because of the substring free property, because if you have Fj starting earlier, like if Fj starts from here, then Fi would be a substring of Fj and we would violate the substring free property. So therefore we can argue that this property is true. Also observe that 2 strings cannot begin or end at same position. So for example, if you have 2 strings beginning at the same position, then again one of the string has to be a substring of the other string, and that would again violate the substring free property. So given these 2 properties now, which are correct from the substring free property, what we can do is now we can build a Hamiltonian path very easily. So what we do now is we build a Hamiltonian path by the ascending order of the starting positions of all the strings. So because the starting positions are now well ordered, we can take one string at a time based on its starting position. So, in this particular example we will take Fi first and then we will take Fj afterwards. So, following this order we can build a Hamiltonian path, and that proves that this shortest common superstring S corresponds to a Hamiltonian path in the overlap graph, because we have given the specific ordering in which all these vertices can be visited in the overlap graph. So, this proves the property and establishes the connection between the shortest common superstring problem and the Hamiltonian path problem. So, now what we can do, because now we have this connection between Hamiltonian paths and superstrings, what we can do is we can look at the weights of the paths. So, for example, let me define something as weights of the paths. That is, if you have a path in the graph, so I would define the weight of that path by the sum of the weights of the edges in that path. So, for example, the weight of the path B, D, C, A is simply 2 plus 0 plus 2 plus 4 plus 1, yeah, so that is 7. So, 2 plus 4 plus 1. So, now we have defined the weight of a path. Now, let us say P is a Hamiltonian path in the overlap graph. Then observe that the length of the string spelled by this path is equal to this expression, that is where F denotes the sum length of all strings in F. So, I am denoting this as a double vertical sign, and I am subtracting the weight of that path, because remember that when we had defined the string spelled by a path Sp, we were not considering the overlaps twice, we were considering the overlapping strings only once. So, therefore, the length of the string spelled by the path is equal to sum length of all the strings minus the weight of that path, right. So, the weight of the path captures the overlaps among those strings. Now, given this property, and from previous property as well, we know that the shortest superstring corresponds to some Hamiltonian path in the overlap graph, right. And given that the length of the string spelled by a path is given by this expression, where this string we cannot control. So, this quantity we cannot control because this is the input. So, F is the input and some length of all the strings is fixed. However, we can choose an appropriate path and such that Wp is maximum, that is the weight of that path is maximum, and accordingly we can derive that path which gives us the shortest string, that is that we can go for that Hamiltonian path which gives us the shortest string. So, in other words, the shortest superstring can be computed using the classic problem of finding maximum weight Hamiltonian path. That is, we have to look for a Hamiltonian path which has maximum weight, and the string spelled by that particular Hamiltonian path will give us the shortest common superstring, right. So, it is interesting to see this connection between Hamiltonian path and the shortest common superstring problem, because the Hamiltonian path problem is a very well studied problem in computer science, and therefore, all the algorithms and results known for Hamiltonian path can be used for shortest common superstring problem as well, right. So, known algorithms for max weight Hamiltonian path can be used for solving SCS problem as well. But it turns out that the known algorithms for solving maximum weight Hamiltonian path are not polynomial time, and that is because maximum weight Hamiltonian path problem is NP hard, So, if we choose this route, then it is unlikely that we can solve the shortest common superstring problem for large inputs, and that is because the maximum weight Hamiltonian path problem is NP hard and efficient algorithms that scale to large inputs do not exist. So, that raises the question, do we have faster algorithms for shortest common superstring, right. So, this was one option to solve shortest common superstring problem, but do we have alternate methods that can solve shortest common superstring problem more efficiently, preferably in polynomial time? But it turns out that the answer is no, because in different results shortest common superstring problem itself has been proven to be NP complete, and that proofs comes from this paper referenced below. That is, we do not have efficient algorithms for large inputs. Now, given this situation, what typically we can do, that is, as done in commonly, we have to look for alternatives, that is either heuristic algorithms or approximation algorithms that can scale to large inputs. So, in the remaining time of this lecture, let us look at one approach for solving this problem, and let us call it greedy algorithm. So, we will look at a greedy approach for solving this problem, which will be much faster to solve. So, let me give simple notations before I give out this greedy algorithm. So, let me denote OV as the length of longest overlap between F1 and F2, that is the length of longest suffix of F1 that matches a prefix of F2. Let me also denote delta out as the out degree of vertex F in a graph. So, that is, if there is a vertex which has two outgoing edges, then its out degree is 2. Similarly, I define in degree of a vertex as, I denote it as delta in. So, if there are 3 incoming edges, then the in degree of this vertex is 3. So, given these basic notations, now let us look at this simple greedy algorithm. So, this greedy algorithm is very simple and it works as following. So, for each string f, we create a vertex with label f. So, we have a graph and we create a vertex for each string f, and that vertex is labeled f, right. So, if there is a string ATCG, then we create a vertex whose label is ATCG in my graph G. And initially the graph has 0 edges. Now, next what I will do is I will consider all pairs of vertices in the graph where the out degree of F1 is 0 and the in degree of F2 is 0. That is, F1 has no out degree and F2 has no in degree, and among those I will identify the pair with maximum overlap, and I will add a directed edge from F1 to F2. So, this is the greedy part where I am looking for those pairs which have maximum overlap. Here I am making a greedy decision based on combining those vertices which have the maximum overlap. I will repeat this step. So, I will repeat this step 2 until we have a single connected component in the form of a chain. So, what will end up happening is you will initially have many vertices, and we will keep on connecting these vertices based on the overlaps. So, we will keep on looking for maximum overlaps, and as soon as we form a single component in form of a chain, then we will return the string spelled by that path. So, it is a greedy algorithm in which at every step I am making a greedy decision based on the maximum overlap length. and this way I will form a chain in the graph, and finally the string spelled by the graph will be my output. So, let us look at one example to understand this better. So, let us say you have 5 strings and you create a graph with 5 vertices. You look for the maximum overlap between these vertices, and we will break the ties arbitrarily. So, in this case the maximum overlap that we see is 2, and accordingly we will add a edge between this vertex to this vertex. Similarly, then we will look for next pair of vertices in which a maximum overlap length exists, and accordingly we will create a new edge. Again we see a pair where the overlap length is 2, and we will add a edge, right. So, we will keep on doing that until we have a single connected component in the form of a chain, right. So, here you can see that we have a single component now which forms a chain, and finally once we have this chain we will output this string spelled by this path. Remember that when we consider the string spelled by a path, we only consider the overlaps only once. So, here this portion will not be considered because we are only considering the overlaps only once when we are spelling the path. So, accordingly for this particular example the greedy algorithm will output a superstring of length 7. So, this is how greedy algorithm is working. At every step we are making a greedy decision based on the maximum overlap length, and we are combining those reads by creating a edge, and we keep on doing this until we have completed a complete path in the graph. So, now this is so far a heuristic algorithm, because so this algorithm is definitely not guaranteed to produce the optimal answer for shortest common superstring, because it can happen that the greedy decision that we make is suboptimal. So, what we are going to do is in the next lecture we are going to analyze this greedy algorithm in more details. So, in the next lecture we will look at the approximation guarantees, that is the greedy algorithm that we discussed, maybe it offers some approximation guarantees to the shortest common superstring problem. And secondly, we also want to know whether if I give you reads as input, is the output of greedy algorithm guaranteed to match the true genome sequence? That is the algorithm, can it be applied on real data as well, and would the output make biological sense? So, we will analyze the greedy algorithm in more details in the next lecture. So, in this lecture we will focus on one approach to solve the genome assembly problem, that is shortest common superstring. We drew a connection between shortest common superstring and Hamiltonian path problem. So, that gave us the first approach on how we can solve the shortest common superstring, but turns out that that approach cannot scale, and in general shortest common superstring is a computationally intractable problem in which fast algorithms are unlikely to exist. So, therefore, we started looking at a greedy approach in which we make greedy decisions at every step. So, that algorithm is very fast because we have to look for pairs of strings and create edge whenever we see a maximum overlap. So, this simple approach called as greedy approach we will analyze in the next lecture. Thank you.